Welcome to this tutorial. In this tutorial, we look into Aspen simulation of a regenerative ideal Rankine cycle with multiple feedwater heaters. If you remember from our previous discussions, we said that we have two types of feedwater heater, closed feedwater heater and open feedwater heater. Most steam power plants use a combination of these two types of feedwater heaters, and the optimum number of the feedwater heaters is determined from the economical consideration. So we need to see if we can save more money from the fuel cost, for instance, than the cost that we need to invest to buy extra equipments. The effectiveness uh, of the pressure of the steam extraction in relation to open and closed feedwater heaters is a crucial factor of thermal system design in power plants. Uh, Usually, open feedwater heaters are more efficient when utilizing low pressure or LP steam extractions. On the other hand, closed feedwater heaters benefit from high pressure steam extractions. Open feedwater heaters operate on the principle of direct contact between steam and feedwater, allowing for efficient heat transfer. So the use of low pressure steam is advantageous because it can effectively raise the temperature of the feed water without complexities associated with higher pressures. Conversely, closed feed water heaters are designed to operate with high pressure steam extractions. The closed system allows for the recovery of the heat from the steam without direct contact with the feed water, which is beneficial in maintaining higher pressure and temperatures. The choice between low pressure and high pressure extraction ultimately depends on the specific design and operational requirements of the thermal system. Uh, when we say high pressure extraction, typically the range of the pressure is something around 10 to 30 bar, and this is suitable pressure for a high pressure turbine, which are designed to handle steam at high temperature and pressure. And the low pressure steam extraction is roughly around zero point 0.5 to 3 bars. There are some general guidelines when it comes to the choice of the feed water heaters that I've summarized them here. In a typical steam power plant, we usually have one open feed water heater, which serves as a deaerator and is usually placed near the middle of the feed water system. The closed feed water heater with drains cascaded backward is the most common type, used both before and after the open feed water heater, and it usually use high pressure extractions. We also have usually one closed feed water heater with drains pumped forward, and it's often used as the lowest pressure feed water heater to pump all accumulating drains back into the feed water line. Occasionally, one encounters one more feed water heater of this type at higher pressure stages as well. Uh, this is like a typical picture of uh, the flow of the different streams in a real steam power plant. As you can see, we have a low pressure and a high pressure turbine and also intermediate pressure turbine. You see that after the condenser, we have one closed feed water heater with the drain pumped forward, and it's at low pressure. We have also a couple of more feed water heaters with low pressure extractions before the open feed water heater here. And then after this open feed water heater, the feed water is pumped to the boiler pressure using a pump. And we have three more closed feed water heater with extractions coming from high pressure and intermediate pressure turbine. and you see that the drains are pumped backward. One useful factor that you can use to check if you have done a proper design is the optimum temperature rise per heater. For a preliminary design of n feedwater heater, the temperature rise through each heater is given by the equation that you see here. T-opt is the optimum temperature rise per heater is equal to TSL, the temperature of the saturated liquid at the throttle pressure. The throttle pressure is the pressure that the superheated steam enters turbine, minus T condenser, the temperature of the feed water that leaves the condenser, divided by n plus 1. N is the number of feed water heaters in your system. So Ti is the temperature after each step is equal to T condenser plus the number of that step I multiplied by T optimum. Now let's do this exercise together in Aspen. We want to simulate a steam power plant that operates on the ideal regenerative Rankine cycle with one open feed water heater and one closed feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees C, and it condenses in the condenser at the pressure of 10 kilopascal. The fraction of the steam leaves the turbine and enters the closed feed water heater. Another fraction leaves the turbine and enters open feed water heater. And we want to determine the maximum thermal efficiency of the cycle with the optimum extraction pressures and fractions. The steam flow rate is 10,000 kilogram per hour. Before we use Aspen for the simulation, let's do some calculations with the optimum rise temperature equation. As we know, the throttle pressure is 15 megapascal, the temperature is 600 degrees C, condenser pressure is 10 kilopascal, and the number of feed water heaters that we have is 2. From the steam tables, we can read the saturation temperature at 10 kilopascal, which is 45.8. The temperature of the saturated liquid at 15 megapascal is 342. And we can use the equation I showed you in the previous slide to calculate the T optimum. So T optimum is 342.2 minus 45.8 divided by 3, two preheaters plus 1. So the optimum temperature rise is around 99. So now if you want to calculate the temperature after the first feed water heater, you add the condenser temperature plus stage 1, I is 1, multiplied by 98.8 is roughly around 145. And after the second one, I is 2, so you use the condenser temperature plus 2 multiplied by 98.8 is roughly 243. Now let's do the simulation in Aspen and check if we can make a proper design using the tools in the Aspen. Let's start from a simple ideal Rankine cycle with one turbine, condenser, pump, and boiler. We want to add two feedwater heaters, so we need two extractions. As I mentioned before in previous videos, it's not possible to get an extraction from turbine directly in Aspen. So we need to make some type of extra equipment here. So we do a trick and we add extra turbines for each extraction. And after that, we extract some steam out of the turbine and then we return the rest to the next turbine. Then you need also one mixer or tank here. If you look to the model plate here, you can either use a mixer, a simple mixer, or a tank for open feed water heater. And in exchangers, you can use a simple heat exchanger for the closed feed water heater. I pause the video, I add the relevant components and streams, I rename them properly, and then we take it from there. So as you can see, I have added two more turbines because we have two extractions. we have the main input. Then we take some of this steam out. We put it in a closed feed water heater, which is a simple heat exchanger, and the rest goes to the next turbine. And then we take some more and we put it in open feed water heater, and then we send the rest to the third turbine. And then the feed water goes to the condenser, passes through the first pump until we reach the open feed water heater pressure, which is the same as this extraction. And then the second pump will increase the pressure of the feed water to the boiler pressure. I also have added one valve here for the drain stream. So the drain stream can go either to the condenser or to open feed water heater. I put this in open feed water heater, and the output pressure of this valve is the same as open feed water heater. Uh, Now I try to add the information needed for the program to calculate the uh, thermal efficiency of the cycle. Now I click on the next button, and we are navigated to pump number one. Pump number one is the pump that transfers feed water from condenser to open feed water heater. So we need also to decide about the pressure for turbine one and turbine two. The extraction from turbine one, which is high pressure turbine, goes to closed feed water heater, and the extraction for the second turbine goes to open feed water heater. For now, let's say that we take 30 bar as the extraction for the first turbine, and for the second one, we take, let's say, 3 bar. And then for the pump number one, we also use 3 bar, which is the same as the pressure of open feed water heater. The streams come from the second turbine, so this should have pressure of 3 bars. So pressure of 3 bar here, and then we click on next to see what else we need to do. Yes, the second pump transfers the feed water to the boiler. So this is the same pressure as boiler, 15 megapascal. Next, we need the split fraction. Let's say that we take like 10% of the steam out in the first extraction and 10% in the second extraction. And then it seems that we have all we need. One more thing, I have also added the parameter needed to calculate the thermal efficiency. I've defined the Q in and Q out. It's the heat duty from the boiler and condenser, and the equation to calculate, we had two equations to calculate the efficiency. One is using the work of the turbine and the pump, and the other one is the Q from boiler and condenser. So 1 minus Q out divided by Q in. I also use the minus sign here because the Q of the condenser, it's a negative value according to the definition in Aspen, because it's released to the environment. And now I click on the next to run the simulation. We wait for the outcome. We have an error in pump number two. Let's go and check what's the error. I think the reason could be the vapor fraction. So I check this pressure, temperature, and vapor fraction, and you see that we have like 10% vapor, 11% vapor that enters to the pump number two. So either the pressure here is too high or the split fraction is too high. We check the flow. Here we have 150 to 30, 30 to 3, and 3 to 0.10. And then the same pressure after the first pump as the open feed water heater. And then we have the uh, input to the second pump, and 150 after the second pump. Here we have another problem. I forgot to insert the output value for the valve. The pressure after the valve should be the same as the pressure of the open feed water heater, which is 3 bar. So this should be 3 bar. So it's 3 bar. The value that I had was not correct. So I click on next and rerun it just to make sure that everything is fine. Yeah, that was the error. So you can see that now everything is settled, and everything looks fine. We go and check the thermal efficiency result. It's 35 compared to 30.4 before with these two feed water heaters. So we have improved the thermal efficiency. We also need to check if we have an optimum temperature rise in our simulation. According to the calculations we did in the beginning of this video, we said that after the first feed water heater, the temperature should be around 145, and after the second one should be around 243. And you see that it's this is not optimum, so we need to optimize this. But how do we optimize this? First, there are two things that needs to be optimized. First is the split fraction here, and the second one is the pressure. For the split fractions, I add two design spec, and then I use TTD and DCA. DCA is already there. I use TTD to rise the temperature of the feed water after the closed feed water heater, and then I use a second design spec for the second splitter, and in that splitter I manipulate the fraction until the feed water that leaves the open feed water heater is saturated liquid. I paused the recording and added the extra component needed for design spec. I've added one cooler and heater here and one cooler and heater here to get the value for the saturation temperature at extraction pressure here and here, because we need it every time that we change the discharge pressure here and here. Then you have a new value, and I need to use that value to do this TTD for closed feed water heater, and also make this output of the open feed water heater as saturated liquid. I have added two design specifications. DS number one is for the closed feed water heater. In that closed feed water heater design spec, I define two variables. The temperature of the reference one stream, this one, is the saturation temperature at pressure of discharge pressure of turbine one, and the other one is the temperature of the closed feed water out stream. And the difference between these two, I put it equal to 3, and I vary the split fraction in splitter number 1 between 1 to 30%. This should be enough. For the second design specification for open feed water heater, I've defined two parameters. One is TREF number 2, which is the temperature of the stream after the second extraction. And then the difference between this temperature and the feed water out should be 0, because we assume that the feed water leaves the open feed water heater as saturated liquid. So I define this as the difference between these two temperature. It should be 0, but I put 1 because we have some tolerance, and we want to avoid having any vapor that enters pump after the open feed water heater. Uh, I have also added two transfer from discharge pressure of turbine number 2 to the discharge pressure of pump 1, and discharge pressure of valve to discharge pressure of the discharge pressure of turbine 2 to discharge pressure of valve, because these two streams are going to the same tank as the open feed water heater. And this is if you change the pressure here, these two should be automatically changed. If you want to put this in the condenser, you just move this to the condenser and put it 10 kilopascal. But I put it in open feed water heater. I assume it's more efficient. Now let's run the simulation to see everything works fine. I also added one more calculator here. We had one before that was the Q in and Q out, and we used this equation to calculate the efficiency. This the second one that I have added is with the work of the turbine and of the work of the pumps, and I use this equation instead. Both should give the same answer. So I run the simulation now to see if everything works fine. Let's look into the results. As you can see, we have no errors. Let's follow the streams. We have 30 bar as the first extraction, 3 bar second extraction, and the temperature rises after the open feed water heater to 132, and after the second one to 231. If you remember, we used this equation to calculate the optimum temperature rise. We said after the first uh, feed water heater, the temperature should be around 145, and after the second one should be around 243, which in this simulation, the temperature is lower. So one way to uh, fix this problem is that, or to optimize the design, is to manipulate the pressure here one by one. The other option is to use the optimization tool in Aspen. I start with the first one, which is manipulating this pressure of the turbine 1 and turbine 2. By looking at the steam tables, we'll see that the saturation pressure at 145 degrees C uh, is 400 kilopascal, and at 243 is 3,300 kilopascal, which means that if we change the discharge pressure here to 3.3, and then the discharge pressure of the second one to 400 kilopascal, then we should get the temperature very close to the optimum temperature rise. I run the simulation once more. Results are available. So now you see that the temperature rise is better now. So here you have 142, it should be 145, and here should be 243. It's 236. It's a little bit low here. Maybe we can change this a little bit more. So let's try 3.5 and see what the program gives. Uh, so run the simulation, and we wait for the outcome. So we go back here. Yeah, this is better now. So you see that at 35 bar or 3.5 megapascal, and around uh, 4 bar, I mean, the temperature rise is very close to optimal. So this is one way to do that. The other way to do this is to use the optimization tool in Aspen, which is in the model analysis tool. So let's do the optimization. Before that, we also can check the outcome for the efficiency. So the result for the thermal efficiency is 36.1, and the numbers are the same for both methods. So we have improved the cycle efficiency. Now let's go back to the model analysis tools, optimization, and create an optimization. We click on OK. And now we insert the information that we need. We need to define the objectives and the parameter that we want to vary. So for the defined, we can use the same variables in as we had in calculator. So we just copy and paste those two variables here. And then the objective is to maximize the efficiency. So we can use the equation that we had here, and we just copy and paste that equation. to the input for the objective. So the objective is to maximize this equation. In vary, we need to add our variables. We have two variables which are both are block variable. It's turbine 1 and 2, and the variable is the discharge pressure in bar. So we know we should be around 35. So let's say that we are between 34 and 36. And then the second one is similar. It's a block variable, and uh, it's turbine number 2. It's the pressure, and let's say between 4 and 5 bar. Uh, I take 0.21 as a step size for this one, and maybe should I take 35 here as well, and then 0.21 as a step size. Now everything is ready. We reset and run the simulation. It might take a few seconds. Results available now. So if we go back and check the temperature rise, it's very close to the optimum temperature rise, and the results for this optimization is also available. 36.1 is the efficiency, and the proper values are given. For the pressure, it's 36 and 4. So that's how the optimization works. You have seen that the using the optimize temperature rise also works perfectly fine. So depending on your need, you can use one of these approaches. Thank you very much for watching this video, and see you in next video.